topic concerned. Today we are going to continue lecture based on the vibration. We are still talking about vibration in 1 degree of freedom, which is on the free dam vibrations. If you remember the last meeting, we already, Alhamdulillah, we already completed completed example number 4. We completed solving the problem by applying the Newton's law. So as for today, inshallah, I'm going to do the what you call it, the equivalent methods. So before we move to the one, I'm going to stop sharing this one. I'm going to pick up another slides. This one. I'm going to share with you here. So this is the thing that we stopped earlier on example number 3, which is on page 379. If I can recap a bit about what we captured a bit about what been discussed earlier. Typically on the Newton's law, as I mentioned earlier, as many of you asking about the assignment for the free undammed vibration, should it be done on the 3 method? My answer is yes, because I want you to expose to all the method. The reason is why when we go to the second degree freedom, we are going to look for all the method applied typically on the Newtons and energy. So many example on the energy, and also so many work on example in the energy and also Newtons. So we are not going to look for, or we're not going to use the the equivalent method anymore. So this is why what emphasize that you need to know the other methods. Even though I know that most of you are keen to solve this one by using equivalent method. For this, typically 1 degree of freedom, yes, but not for the next level of the vibration. So that's why I hardly see that you have to do on the 3 method, or typically for the undamped vibration. Okay. So here we are going to look for Newton's law, for example, as I mentioned earlier. This is the simplification of what we've done earlier, just to recapture things that we discussed so that you can catch up where we stopped. So first, what you have to do is to construct free body diagram as usual, because we are dealing with Newton's law. Isn't it? Newton's law, you must have free body diagram. This one is not. This one is with pendulum effect, and with pendulum effect. With pendulum effects. So if you can do this one, this is the initial, this is what we call equilibrium position. So equilibrium position is anything by the one, and you displace a bit, a very small displacement by saying theta dot and theta double dot. It seems that these 2 parameter, or these 2 K and C, will not allow you to move what we call this one restoring energy. This one also have the restoring energy. The restoring energy is basically what energy bring back from the displaced position to the initial position. So it seems that you have here one Kx, the other one you have Cx dot. Here you also have another one, because you have the energy, because you are concerned about the Newton's law, so you will have mg sine. So these are all the restoring energy. We call the restoring energy. Okay, this is about O. This one hints about O. So you have to use summation of moment about O, IO, theta, double dot. Isn't it? It's not very difficult. Then you start saying that, okay, anything that move that way, clockwise or counterclockwise from your seat, that we can see that's positive as what you've been displaced to this one must be the same. Then you have, okay, we have negative Kx multiplied by the distance, isn't it? It's here 0.065, right? Minus by Cx dot multiplied by. So before that, you need to know that you have a small oscillation. Remember, small oscillation. For small oscillation, we are going to ignore, perhaps saying that the sine theta equal to theta cos theta equal to 1. for the small oscillation. Yeah, so you see x dot by 0.1 minus by this one is mg sine theta by this one be 0.065 equal to the I. This I will be, you have A, I about O, sorry, I about B. This one about B, yeah. This one's about B. I thought about A just now, sorry, yeah. This one about B. So you have I for this A, correct, about B. Then you have plus this I for this lever itself, the lever itself, plus I lever, or perhaps I can put it ABE, plus the small portion of mass on the dashboard, yeah, is I, we call it IA. So you have this one, all I's here. I about B theta double dot. Okay, then finally you need to know what X is. So your X is basically representing by the segment equation is 0.5 by theta here. So 0.5, sorry, it's not 0.5, it's 0.065. Yeah, it's 0.065. It's a 0.065 theta. And you have 6 x double dot, put it the x double dot, is basically 0.1 theta. Don't worry about this one. What you have to understand this one is this one basically from what? From segment equation. Segment. So you put in here. Okay. So finally you be getting the results of equation where you have theta double dot plus this one c by m theta dot plus k by m theta equal to 0. So you will be in that particular equation. We call this one equation of motion. Okay, this one we already completed. As for today, we're going to look for this one by energy methods. By energy method, and you know well then energy method cannot be applied. So energy method, put it here. Energy method cannot be applied as energy is dissipated. Energy dissipated. It simply means that, or in other words, d by dt ke plus pe is not equal to 0. Okay, it's not equal. So we cannot use energy method. But it is so different when you are talking about, even though you be oscillating, yeah, but we assuming that the energy will be the energy will be constant if you use the Rayleigh method, which is not part of your syllabus at the moment. So you use Rayleigh method. Okay, this one you mean, inshallah, in your 2 degree of freedom. Okay, so we're going to no, you are not going to this one. So we're going to use the equivalent method, equivalent method. And I did mention about some book called as Lam-Mesh system. So you need to simplify this one. So simplify. Before you simplifying, you need to check on point of transfer. You have what? You have A. We put it just A. You have D. You have E. So B cannot be point of transfer. So except with the rest, yes, yes, and yes. Okay. So let's now compare. Let's now, because at the end of the day you'll be getting the same result. So let's say that you have D now. You have D now. Okay. Let's put there. Okay, I'm going to take D. So now take D as point of transfer. So your system will becoming, put it here, yeah. So now D as point of transfer. Hello class, can you follow me class? Hello? You from the other side, you can follow me. If anything you feel that it's not, thank you. Yeah, if you feel that anything is not correct, just speak up. Or I basically I can't, I can't catch whatever you write. Yeah, you can speak up. Yeah, I allow you to speak up. So now, if D will be part of your point of transfer, for example, then I'm going to put everything in B. So now transfer all, add or to D. How is it? So your system becoming, you can simplify this one, you're becoming here, isn't it? So this one is in at one point, point B, will not change. This one is the distance 0.065. And we have one mesh, two mesh, we have three meshes, isn't it? So you put three block here, three block one. Okay, it's not enough space there, so I'm going to put it a bit down here, so it will be adequate space. Yeah, okay. Again, 0.065, 1, 2, 3. So what are they? They are MA, put it MA, you transfer, put it prime. You also transfer the MABE. This one is MABE, put it prime. And finally, you have ME, the small mesh there on the dashboard, which is not, you need to solve this one from D to E, so put it ME. Isn't it? So the system is controlled by remember, yeah, this is not free body diagram. Remember that this is not a free body diagram. This is a simplification model of the given model. We simplify those. It's not a free body diagram. So you can put this one here or the other side, doesn't matter. Okay. This is C. It is not C, but yet it's a C prime. It is not K, but yet it's K prime. You can put it KT, you can also put it CT, T mean total. This one, the whole lot becoming MT prime. Okay, then only the equation, this equation valids. What are the equation? Number one, the omega n K by M is now valid to be used, but it is not K, but KT prime MT prime. Number two, yes, CT is equal to 2m omega n zeta, isn't it? But it's not C, it is CT prime, is MT prime. Okay, so this equation now is valid to be used. Remember this equation? This equation is belong to one plane equation. So we are simplifying this one to become one plane, isn't it? Okay, now. So the question asks us to define the omega n. It's so obvious. So you need to know what be KT and also MT. So now start transfer everything at this. So mass, put it there, mass. You have mass of now mass equation. Remember, I initial equal to I equivalent, isn't it? So the I initial typically for what? Pick up one A for MA, for example. I initial is basically the ME multiplied by the 0.065 power of 2. Isn't it? It's equal to, or perhaps I put it in the equation first, then I put all the numbers, yeah? So that you can understand where the numbers come from. Put it here. Okay, this is MA, correct? MA multiplied by AB power of 2 is equal to the MA. It's no longer MA, become MA prime. Then you move here as B, D power of 2. And you put the one, then you understand, oh, so this MA given MA as 8, the distance from A to B is 0.065. Then we transfer this one to become MA prime to the new distance, which is 0.065. And you found that you become, same thing. It's exactly acting like the moment, isn't it? So no change. This one, no change. Why no change? Because AB is equal to BD. Now we move again to this one. I put it another color here, so I get another one which is MABE. So this one is MABE. Put it prime. Class, hello, are you follow? I don't know whether. Okay, thank you, Lee. Yeah. Okay, now ABE sounds. So the concern is now from, remember that I did mention about equivalent method when you have as such. We are going to what? We are going to change this one from the physical manner of the crank lever to become as such, without changing the point of transfer. This one still at B, but now becomes one. If this one is M, this one become M. Right. Okay, so we have K M ABE as mentioned here. If I can put this one away, so you have what is MABE is a 2.5. The crank lever has a 2.5 kg. This one 2.5. Put it there 2.5. So I'm going to give this one a bit thicker. I'm going to move to this one. So 2.5. So we have 2.5. The K here is given here. 0.05 power of 2 is equal to the new MABE. Now the new is to be 0.065. This is the new length or the new distance from B. Okay, any question? Anyone? No? Okay, now, so if you simplify the whole thing here, so what you'll be getting? You'll be getting the result of what is, you have a numbers MABE. So if my calculation is correct, I'll be getting inshallah 1.48 kg. Okay, 1.8 kg. Okay, now what else? The small m, ME prime. ME prime given here as 0.5. So put it there 0.5. So the distance is 0.1. This one power of 2, yeah, power 0.1, right, equal to ME. You bring to 0.065 power of 2. So that will give you ME prime is equal to, you do this one, calculate that one, you'll be getting inshallah 1.8. That's correct. Eh? What do you get for the one? You'll be getting 1.18 kg here. So here. So the total mass here will be M total. M total prime is equal to the whole thing. If you add up all together, you get 10.66 kg. Okay. Alternatively, remember the I naught, we calculated I naught. It's not I naught, sorry, I and about B. Remember, if you go back to the your solution earlier, you found that IB is what is here? IB is 0. You check your notes, yeah, 0.045 kilogram meter square, isn't it? Yes, no. You turn to page we done earlier in our calculation. I remember this was 0.045 kg. So we use equivalent method. So I initial is equal to I equivalent. So this I 0.045 is equal to this I equivalent. So we have the I equivalent is basically the MT equivalent multiplied by we move at D, isn't it? So we move at D, you have BD, this one is D, yeah? BD So this one is BD power of 2, or perhaps the MT prime is equal to 0.045 divided by 45 divided by 0.065. You'll be getting, inshallah, same results. Okay, so you can use this one. This one is, if you don't understand this one, never mind. You use as a normal what calculation. This one just to double check your result. To double check your result. Okay. Basically, it is the same, because you need to know what the IB. But we are very fortunate because we already calculated the IB earlier in our first solution. Okay, that is M. So the next part is to define settle. Sorry, M is settled. Then we need to look for the KT. So KT now. KT. The KT is one split spring. Okay, spring is delta PE elastic initial. This is the what? This is the equation. General equation is the equivalent. You have the K now, where your K is only 1K, isn't it? So your K is KT. So basically what you have is this one is, I put it there as K prime, for example. So your K prime multiply 0.065, isn't it? Equal to, sorry, it's not K prime, astaghfirullahalazim. It's K, yeah? It's the initial one. This one will be K prime, this one will be 0.05. So you don't have to do this one basically. This one just to check whether it's correct or not. So therefore, you need to know that KT is basically K, is equal to, been calculated as the K. Where is the K? See, you can read the equation here. So the K is given by 5 kilonewton. So this 5 kilonewton, 5 kilonewton. Yep. K prime is not K, the K prime. So K prime equal to K equal to 5,000 Newton per meter. But you also have another one, remember? Remember this one? This one, you have another one here. What? You have a spring here, remember? Effect from the pendulum. So the KT is basically equal to the K plus the KP, but KP will be at A prime. What, you know KP? What is KP? Class, do you know what KP is? KP is basically the stiffness metric, stiffness of spring representing the pendulum, effect of pendulum. So you have the mg divided by L. Hello? Can you understand me that, class? Why so quiet? Yes, Fadil. Thank you, Fadil. So this one is where this one come from? It's from the static equation, where you have mg equal to mg to k delta. Now we put it here. So you have another a spring representing the kp. So kp, so put it kp prime. So the kp prime is kp, is it? Kp equal to the mg. You need to know. You need to find this one first. If my calculation is correct, yeah, put it kp equal to 0.065 square plus, you have another one is kp prime. Now you bring kp from 0.5 to 0. From where? From here to same one. So you have the kp and also kp. Kp and also kp. Okay. So basically your kp prime is equal to the mg. This one calculated earlier. I forgot the what you have. The mgm is. Could anyone remember? If I remember, just remember the numbers is here. I get 4.7.4 Newton. So your kp, so your kt prime now become, the k will be 5,000 plus The next one is 1207. You'll be getting a such number of 62607.4 Newton meter. Okay. Now we can now calculate the omega n, but let us now go further to look for damper. You do the transfer one time only. Then we use all the parameters to solve every problem. So this one is delta VD damper initial is equal to delta VD damper is a equivalent. And you found that the damper is located at here, isn't it? So at E, so the distance of 0.1. So you put it here. This one is the C at E prime. So C at E, this one is 0, this one is BE equal to C at E prime. You move from BE to B, D square. So you have this one, CE is equal to what you have is, you will have the CE is equal to CE. This one will be 0.065 divided by 0.1. The other way around, it's supposed to be this one, 0.1, yeah? 0.1, 0.065, power of 2, you're getting a result of this one. So that will be in terms of 2.367 CE. Okay, so that will be calculation about what we're going to do next. So now, therefore, first is to define omega n. Omega n is kt prime divided by mt prime. So you bring the whole thing. What you calculated earlier was 6207. 6207.4 divided by your m is 10.66 just now, 10.66. That will give you the result of 24.13, same as before. This one is same as before. Number one. Number two, the question asks us to define what C, isn't it? Right? Look at number two. Define what is the constant, the damping constant C. C is equal to 2m omega n zeta. And it is not C here, it will be CT prime and MT prime. So this one CT, you have the result. You don't have, what you don't have is basically the omega n. And yet we are going to look for, look at the equation, ask you to define what? The critic constant for C now is basically for that. So you need to find zeta. From earlier calculation, remember zeta is 0.344. Remember the equation? Ln x1 divided by xn is equal to 2 pi n zeta. This one is 1 minus zeta square. So you'll be getting zeta as that. Isn't it? By knowing that your n equal to 1, your x1 is always 1, and your xn is equal to 1 upon 10. These are all given parameters. Okay, you have this one. So the next thing that you don't have here is basically what will be the CT here. But remember here, when you look the result of CT, look at this one, is CT is basically what? Excuse me, CT is basically only CE prime. So put it here. So CT is equal to, CT prime is equal to 10.66 by 2413 by the 0.344, that you have this one. So if you calculate that one, so that will bring you 74.74 Newton second per meter. Okay, and yet for our calculation earlier just now, you have this CE. Okay. The next one is to define omega d, a critical damping. It's not very difficult. Remember the critical damping? The critical damping number 3, yeah, the critical damping is basically, remember, zeta is always what? C by Cc. You know the C, put it here, you know what will be the Cc, and you believe that Cc will always greater than Cc. This is why you can do on your own. It's not very difficult, isn't it? So you be getting also, you be getting here, okay, Cc is basically coming here. Cc is basically 74 by 74 divided by 0.344. Big thing, that's what the result. And last but not least, when you have the 4 here, you have omega d is equal to omega n 1 minus zeta square. Is exactly same from last calculation. Okay. Any question? So we can move to the next one. Okay, let us now move to this one, the second one, example number 4. So example number 4 and example number 1 is exactly the same. The only difference now, this one pointing upward, the early one is pointing downward. Look at here, the pendulum is pointing upward. Look at the previous one, the pendulum is pointing, this one pointing downward, this one is pointing upward, isn't it? The spring, both spring and damper now at bottom, this one is at top. All the distance, all the parameters are all the same. So in conclusion, the only difference now here the pendulum effect as the restaurant energy on it is not being considered. Why? They mention the neglect the pendulum effects. So if I can do this one very quick one, yeah, very quick one. So you'll be getting a result of Newton's law, for example. Newton's law. So you have, okay, you have this one. So you displace theta dot theta double dot. So you have, of course, as I mentioned earlier, this one you will have kx. You will have this one cx dot. You don't have this one pendulum because we neglect the pendulum. So your equation now becoming summation about b, still about b is equal to I b theta double dot. Isn't it? So we are going to ignore the pendulum for the mg term. So anything that we consider as positive. So you are saying that negative kx. Oh, sorry. It's supposed to be pointing the other way. Never mind, just check this, change the direction. Yeah, pointing that this one. So this one be negative kx, negative cx dot. Again, I missed one point here. So kx will be multiplied by the distance is 0.065. This one 0.065 minus by cx dot 0.001. Then there's no mg here, equal to I, whatever I at b now theta double dot. The equation now become shorter. So the rest are the same. Okay. Same thing for when you do the equivalent method. When you try to solve, for example, yeah, you're trying to take care or take E as take E as point of transfer. So your problem now become, look at here, how many masses? You still have 3 masses. You still have 3 blocks. At the distance of 0.1. This is about B. So you have the MC will not be transferred. MC will be remain as MC. You will be transferring MA here, MA prime. We're transferring MABE. Then this one will be The C will be remain as C. Ct prime is equal to C, but yet Kt now is equal to K prime. Okay, so no Kp. Remember that, no Kp. Okay, you can do this one on your own, correct? You try to do this one. This one not very difficult, but introduction only. So if I can move to the more challenging part, example number 5, for example, look at this one, this one. So the difference of this example compared to the previous one, you found that you have two, what do you call it, two fixed point. One fixed point will be here, the other will be at two fixed point here. Okay, the previous one only one fixed point. Where are the point? The previous one is the B will be your fixed point, isn't it? This one also B will be your fixed point. This time fixed point is not, it's not the per se that is a fixed point. Like this one is a fixed point. No, the meaning of fixed point in vibration is basically the ability, or perhaps the system can rotate at that particular point. This one, yeah, this is the one. The system can deflect it, can rotate at this point A. And O, same thing. The system or the whatever you have here can be rotating about O. Okay, not this point and not, so this is not fixed point. But when you see per se this one, this is a fixed point. No, the fixed point here, the definition is when the system can rotate or oscillating at that particular point, we call it a fixed point. Of course, it is a fixed point per se. Okay, now when you have this one, you have some other parameter. Again, yeah, this one is if you apply Newton's law, for example, the very long solution. If you can pick up the solution from your book here, pick up your solution from your book. I'm going to look for your book here. One more minute, yeah. I miss my book. Okay. This one will dealing with kinematics. A lot of kinematic will be, considered here. The reason is why, because you have two fixed point. One will be here, and the other one will be at O. Look at here. This one at A, one fixed point. The other one is at O. Okay, so by Newton, you have to construct this one. This is what we call the kinematic diagram, or some call as the kinematic relationship. It is not very difficult. Look at it. It's very logic here. If you want to solve this one, it's very logic. Look at it. First, it will be at this position, isn't it? Then you displace. You displace downward. You displace downward. Rotating that point. So this one be considered as theta. Can we put theta 1? Yes. Okay. Then you have the distance is 0.2 and 0.3. You have this one. Okay. This one you'll be getting the result from what? From S equal to R theta. So you have x1. Put it there, x1. Can we put x2? Yes. x1 equal to, we have the distance 0.4, 0.3, becomes 0.5 theta. Theta what? Theta 2, because you precisely prescribe this one as theta 2. Put it there, theta 2. Can we put theta 1? Yes. You can put it theta 1, doesn't matter. Okay. Why I put this one kx1? Because I have a k1 here. If I put it x2, you have k1 and x2, a bit confusing. So k1 and x1. Okay. Also c1 here. It doesn't matter this one theta, yeah, doesn't matter. So now you have one relationship. The other one here, because you know that the cord is inelastic. The cord is inelastic. Elastic. As the cord is inelastic, you know that the tension in cord is always be the same. So you cut the cord here. You cut the cord or the wire so that you can create or you can construct the free body diagram. So this one is F, this one also F, pointing each other because we have two force member here, right? So now why it is pointing upward? Because you displace one downward. So this one will not allow you to move. We call as a restoring energy. It's pointing upward. Okay, so now you have the equation. Look at how the equation generated. for rod ABD. This is what ABD. You have this one, as I mentioned earlier. You have the theta, the x2. Sorry, you have the x1 and also x2. X2 will be in another here. X2. Okay, x1 and x2. This one x1, x2 will be a small portion. Theta. One for the this itself. When this one be displaced, this one be displaced downwards. So this one also displaced downward. Put it at theta 1, theta 1, theta dot 1, theta dot 1. So you have a small portion connected to that one. So yeah, this one, yeah, small portion here. Put here this one another, what we call it segment equation. So you have xk2 x1, c2 x1. So where your x1 be this one x1. Then you check the relationship between this one. You need to know what be the x1 and x2 because this one you don't have x1 sorry. You need to know what is theta 1. Your aim is here to look at what is theta 1, what is your theta 2. Then as you play around with the equation here, you be getting this one theta 2, you be getting this one theta 1. Okay. Then only you start doing here this one. This one is not very difficult. Look at here, it's not very difficult. This one, it's not very difficult. You've done this one so many times. How is it? Look at here. For the rod itself, look at here. For the rod itself, moment about O. This one, moment about O. Look at the moment about O. What you have the moment about O? You will have, what you have is this one multiplied by the distance of their own, isn't it? Multiplied by 0.2, correct? So you will have negative kx1, negative, just look at here, this one. This one is moment of spring and dash or damper. The other one, you have another one, K, F here, multiplied by 0.3 and 0.2. You have 0.1 here. Yep. Oh, that one is equivalent to another one, equivalent to another one. F1 equal to another one. Okay. So for the this itself, same thing for the this itself. So you have F multiplied by, yeah, this one about A. About A, one about O. I think this one is not correct, yeah? Look at your solution. This one is about A, this is about O, A, this one about A, this one about O. This one is supposed to be about O is correct. This one is supposed to be about A. This one, if you want to do this one, yeah, you have to F just now 0.2 and 0.5. 0.2 and 0.3.5. So if I can draw here again, yeah, look at here how I'm going to draw this one. It's not very difficult. One portion for the what for this what do you call it, for the rod displace. We try to ignore we have another one, this isn't it? We try to focus one at a time. So this one is point A. Now you displace one by theta 2. This by theta 2. You have theta 2 dot, theta 2 double dot. This one, my writing pad is not very smooth here. So you have another spring here. So this one is spring K. You have K1 X2, K1 X2, plus you have another one just on C1 X2 dot. Okay, and this one will be, this one is a 0. Look at here, 0.2 and 0.3. We have 0.5. But remember theta what? Theta 2. And put it there as A1. And this one connected, you have F. And this F also belongs to that F. This M must be equal, isn't it? So now you will have, okay, moment about summation of moment about A equal to I about A theta double dot. And putting here as positive. So you will have F negative F multiplied by 0.5 minus by this one is K1 x2 multiplied by 0.2 plus a minus, sorry, C1 also x2 dot multiply by 0.2. Then there's only the forces acting on the system, isn't it? So that equal to, put it there, is equal to I about A theta. It's not very difficult, isn't it? So then you open up the bracket. What is K? What is X2? X2 is equal to, this is X2 just now. You have negative F. What is our aims now? Is to look, our aim is to find F, equation of F. To look equation of F. So you have F minus by K1. They provide you K1. Yes, 4,000. Put it there, 4,000. You don't have basically to follow all the steps, yeah, because my solution will be step-by-step solution. What will be your X2? Your X2 will be, here is X2, isn't it? Is 0.2 theta 2 multiplied by 0. Okay. What you have? What else you have? You have plus minus by C1. What they provide you C1? They provide 500. Okay, put it to 500 multiplied by X2 dot. X2 dot will be 400. Then X2 dot will be here, isn't it? It's a 0.2 again. 0.2 here, yeah. Theta dot another 0.2. Another 0.2. Correct? So it's equal to, this is I. So what I representing only the what, only look at the equation. Only what you have is only what you have is only what you have is only what? Only here. So about A. So now you know that using, this is I, yeah, I about A. This I, I'm going to focus for I here. This I is basically is for the I rod about what? About A. How is it? You have this one about A. About A. This is A. So isn't it? So what you're going to do next is to define what the mass moment in inertia. Remember mass moment inertia? What is that? What is the mass moment in inertia? For the I when you are taking at the end. If you forget what's one, don't worry. You use what? Parallel axis theorem. How is it? Is I required is IA equal to I center mass plus mh square. Correct? So I required at A, I center mass will be here because this is the uniform rod. You found that is equal to ml squared divided by 12 plus m. H will be L divided by 2 power of 2. Then you will have here ml squared plus this one ml squared, this one by 4, this one by 12. So you bring the denominator equal, so you have just 12. This one will be 4 ml squared, so equal to 1 by 3 ml squared. But if you remember this one, you just put it here. Okay, IA is equal to 1/3 ml squared. Take this one and put it in the equation where you have this one is I can clear this one, put it in 1/3 of ml squared. What is the m? Is basically the mass of the rod. 1/3 m rod L square theta double dot. Okay, so you have the equation. So if you solve this one, you'll be getting F, isn't it? If you look at the solution, yeah, you'll be getting F. Finally, you'll be getting F. F equal to something. Okay, then you do another time. Now you're focusing on the this, on the this here. Where are you? This? Oh, sorry. Where this? Up here. This. You display this now. Become theta 1 dot plus theta 1 double dot. And you have the radius of the disc is given by 0.1. And you also have this K2 and A2 here. isn't it? You have K2 and A2, and this one is acting like K2. It will be pointing downward. It's always opposed the motion, pointing downward. Kx plus Cx dot at the particular point. This one is K2. This one is C2. Then your equation now become, if you can solve the equation, yeah, summation about just now. 1 minute, yeah. I draw it again just to share with you. It's not very difficult. This one will be theta 1 dot, theta 1 double dots. Then this one here you display just now by force. So you have force here, F. So you have here always oppose the motion. This one will be K2x2 plus C2x2 dot. This is about O. So summation about O equal to IO theta double dot. Saying that, rotating that, we consider as positive. Okay, so you have what? You will have this one F. Put it here in another color so that you can differentiate the working. So F here multiplied by the distance is 0.1. Minus by, you have this one is K2. X2, remember X2 is basically 0.1 theta 1, isn't it? Kx2 will be 0.1. It's not 0.0, 0.1. 0.1 theta 2 dot theta 1 dot theta 1 dot. So you apply here K2 is equal to whatever you have. K2 is 12,000. Put it at 12,000 multiplied by the X2 will be 0.1 theta 1 multiplied by 0.1 because we are dealing with moment. Minus again, you have C2 multiplied by 0.1 theta 1 dot multiply 0.1. That's about it. Equal to this I. And remember this I? This I representing I for this radius given. So I for this equal to half mr square. Put it here. Half mr square theta double dot. Theta what? Theta 1. You have another equation, but remember your equation now will be in terms of theta 1 and theta 2. You have two one consistent parameter, which is all in theta 1 or perhaps in all theta 2. So if I can go back to the solution here, you found a solution. So it is basically equating the equation from this and also from the rod. This one is two equation. One is from the other one is from this one. Yeah, both. Here and also the other part here. This is the equation now. All now in terms of theta 1. Then you cancel F and F, isn't it? Because this equation is basically from one single long equation coming from the angular and also torsion twist motion. So you equate the two equations becoming only one single way. Your F will be vanished. Why F is not here? My question: why F is not here? Here is in the equation. Why? Anyone? Why F is not there? It's not in the equation. Why? Because remember, yeah, you have to get rid of F now. Why? Cancel off, correct? In practical, why? Why F is not there? In practical, I know that the canceling because due to the one equation, but why F is not here? In practical, in mathematics, it's correct because F is being cancelled. Correct, it is correct. But in practical, why it is not here? Because what? Because anyone dare to answer? If you don't want to answer this one, I just keep it like that, so that you can check on your own. Anyone? in mathematics, yes, it be cancelling off automatically because you have two f and you equate one f and the other one is negative f. It is correct. But in the present of vibration, for example, yf is not here. Because yeah, sometimes when you make a wrongly a sign of negative positive, you have f here. But you have to know that you have to get rid of f. Yeah. Okay, anyway, because we are not interested in knowing about f, so let me not proceed. Yeah. You get rid of f. You have one single equation. Then this equation now is what is equating by here. This is the differential equation of motion. You equate this one, you be getting the results. Just remember that if you have two fixed point, you have two equations. You have three fixed point, you have three equations. Fixed point is the point that you can rotate all the parameter. Huh? Okay, I know that you are not interested to do this solution. If you see the other solution, which is more simpler. Huh? We define as usual the omega n. Then you have to look for from this equation now. Then it's very easy for us. Yeah, look at now. Let me have the equation now. Let me have the equation. So I'll be getting the equation. I will share with you how we are going to solve the equation. Theta, let now theta 1, theta double dot plus, you have the equation of 52.5 theta dot plus, another one is 2369.7. This one will be theta, of course, and all are basically, representing the theta 1 equal to 0. And we are going to equate this one with theta double dot plus, remember the equation that we did earlier, this one is theta dot plus this one is omega n square theta equal to 0. So by equating this one, you will be getting inshallah the omega n. This one, omega n is equal to the square root of 2369.7. We're getting this one, which will give you 48.7 radian per. And the next thing is the question asking you to find damping ratio, for example, isn't it? So damping ratio will be presented by the second term of the equation. So if you look at the second term of the equation, you pick up this one, second term of the equation. This one is the second term of the equation. Of course, theta 1 and theta will be cancelling. Yeah? So you have 2 zeta omega n is equal to 52.5. And you know well that 2 zeta is zeta, but omega n you calculated earlier by 48.7 equal to 52.5. So you'll be getting zeta. But always remember that whatever you get, zeta must lie between 0 and 1. Otherwise, it's just not correct. Must be greater than 0, must be less than 1. Okay, the next one, what? Omega d. Obviously, omega d, omega n, 1 minus zeta. Also not very difficult. What else? The TD itself, the TD equal to the 2 pi by omega d. Or perhaps in other, term will be 1 minus zeta square. The new thing now is, if you look at the fifth equation, the fifth part of the equation, you found that they mentioned about ratio between, look at the ratio between, this one, ratio, critical damping, this one, ratio between the amplitude ratio after one complete vibration. Critical damping shouldn't be a problem. Yeah, I'm not going to do critical damping. So the amplitude ratio will be after one complete vibration oscillation. So you will be using, inshallah, here, look at here, this equation is equal to 2 pi, this one n, this one is zeta, 1 minus zeta square. Okay, the ratio, remember the ratio. So you put it here, ln x1 is still by xn. Don't worry about that one, just worry about the second, the right hand side equation. We have your 2 pi. How many oscillations just now? 1. What be the zeta? We calculated zeta as 0.54. You put it here, square root 1 minus 0.54 power of 2. You be getting the result of here will be, if you calculate the one, that will give you 4.03. I'm collecting the numbers result from books, from my book and from your book, 4.03. So this is now finally ln x1 xn equal to 4.03. Then how to inverse? You have the x1 by x3 is basically exponent of 4.03. This one is no big deal. Just punch in the numbers in the calculator. But if the questions ask you something else, for example, let's say now let's say the question asks about what is the amplitudes of what is the amplitude after one cycle operation? Amplitude after one complete vibration is typically asking about x2, or perhaps what will be your x2, isn't it? Because one complete vibration, we have only two amplitudes. So from what you have here, you have what you have, put it there another color. So you have ln from ln x1 by x2 is equal to 4.03. Hello? Anyone would like to ask something about this one? You write something, but I just can't figure out what the thing that you have written, that you wrote. Anyone want to ask? You can speak up. You can on your mics. Nope. Can you follow class? Hello. 48 candidate in my class. No one that answer. Okay. Okay, now ln x1 x2 equal to 4.2. So the question asks you, what is the amplitude of one? The amplitude after one complete vibration. So now from here, so now let x1 equal to 1, because since the amplitude is normalizing. So therefore, you have ln 1 divided by x is equal to 4.03. Okay, then you will have 1 by x2 is equal to, if I have this one, we have 56.24. So therefore, x2 is equal to 1 by 56.24. That would be the value. Any question? Any question, class? Hello? Oh, yep, thank you. So the other solutions, we are going to look for another solution here. I'm going to put it what they call it, the working template. I'm going to use another working template here. So the working template will be an example number 4 here, isn't it? Example number, what example? We have example number 5 here. So I'm going to pick up example number 5. Example number 5 here. So I'm going to solve this one by using by equivalent methods. Energy method, now we are not our interest. So to define to solve by using equivalent method, EQM is equivalent method. So now you select point of transfer. So because you have two fixed point, you have no choices here. Basically, you have to pick up the point of, since put it there, since there are there are 2 points of transfer. So select F and D as point of transfer. As point of transfer. Since this point is what? Connecting point. Connecting point. Very important, this one. Connecting point. Here is your extra note, yeah, just to just to answer or perhaps to what do you call it, to give reason why we select FND. It is not simply select FND. I think a couple of times I did mention it in my last lecture. So I'm going to select D here or F here because F and D is basically belong to the same pyramid because it's it belongs to the chord. So this one will be simplified as what you have this one. So first calculate how many mass you have. One mass, M1 mass, M2. So you will have two. You will have what? Two block M. Put it there M rod. Put it there. Just put it M rod prime. The other one is M cylinder prime. Rotating about this one will be about A. But the cylinder itself is not rotating about A. The cylinder is rotating about O. Okay. The rod, yes, rotating about A. But the cylinder is not rotating about A. The cylinder is rotating about O. So put it here O. So the next thing will be, you will have, as usual, K and C. So your CT prime is basically coming from the C1 prime here. Move here from B to D. You have also another one, C2. So you don't have to do anything about C2. So C2 is what? No change in C2. Yeah, put it no change C2, no change C2. Why C2 is no change? C2 no change. Why C2 is no change? And even K2 also no change. Why? Could anyone tell me? Why C2 and K2 is no change? We still pick out the same thing, the same number. Could anyone tell me? Anyone? Connect directly. Correct. Yes, correct. Thank you, Lee. Because it's connected directly. So since connected directly. Direct to point of transfer. So that is the result. That is the reason, yeah, why C2 and K2 is no change, because it's directly connected to point of transfer. So here you have K3, sorry, KT prime is equal to you have K1, yes, you have to bring K1 prime and K. So and these two masses will be representing the MT prime. So if you can simplify this one and you understand where it will be the point of transfer, it shouldn't be any problem. It's very, very easy for you to move on the calculation. So now you're going to what? We're going to do mass. Equation used is I initial equal to I equivalent. So our interest is to look at what? To look at MAD, for example. Yeah, this one is M rod. Put it the M rod prime. Our interest to define what the M rod, for example. So the M rod is basically pin or pivoted at A now. So you have 1/3 ML square. But if they provide you the numbers or the value, it's better still. It's easy for us to move on. Look at there. What they provide you? The consistent 4 kg. Then mass 8. Okay, so you will have this one 4 kg. If I can simplify this one, yeah, so put it there, 4 kg. The distance of L is 0.5. Is equal to I, or is equal to what? Is equal to Remember, you have a rod here. We don't want this. We want to change this one to become, we maintain the L to become lam. Here this is 0.5, this one also 0.5, isn't it? If this is M, this one is not going to be M, but going to be M prime. If this one is 1/3 ml square, this one is not 1/3 ml square because this one is the massless and this is the lam mass. So this one become M prime L square. Okay, so you put it here. Okay, you have M rod. The L square is 0.5. So you'll be getting this one. The M rod is equal to something kilogram. Do you understand? Hello? So you'll be getting 1.333 kilogram. Okay, now we move to this now. This M rod, so M cylinder, put it in M cylinder. M cylinder prime. What is the initial mass moment initial is half M R square, isn't it? And equal to, remember, you have M prime R square. This one is M prime L square. So you have here half mass given by 8 just now. Radius is, put it here half. It doesn't matter, the width without radius is equal to this M prime, this one also R square, we maintain the radius. Then we have the M prime equal to 4 kg, where your M prime is the M cylinder. Or in other words, yeah, basically come from this analogy. You have what? You have this one, I equal to half M R square. You don't want this. You want to change this one to become lam. But you will maintain the radius of R here, So if this is M now, this is no longer M, it's becoming M prime. So your equation becoming M prime, this is I, yeah, about O, for example, about O, this is also about O, equal to M R square. So even though the R is not provided, doesn't matter as long as you keep R constant, so you can cancel both initial and also equivalent. Okay, so if you do this one, have fun, you'll be getting the M total. M total here prime is equal to 5.33. Okay, settle. Okay, now spring equation delta VE. This initial is equal to delta VE equivalent. Initial is basically this initial. Then you move to here, isn't it? So you have K1 multiplied by initial B 0.2. Not to forget power of 2. Then you move K1. As you move K1, there will be no longer K1, it becomes K1 prime. And also, as you move, you have a new distance, isn't it? Or new length is 0.5. Wow. Then you have K1 prime is equal to K1. They provide you K1 as what you have for K1. They provide you K1 as 4,000. Put it at 4,000. This one will be K1 is 0.2 divided by 0.5. That will bring you to 640 Newton per. Okay. Then we have another one, K2 here. Put it there. Okay, this one is K1 prime, K1 prime. Put another one, K2 prime. So the K2 prime now, K2 here, multiply, it's not multiplied by 0.5, is it? Because it's not rotating about A. Now put it there. This one will be rotating about O, this one will be rotating about A. It's two different things, isn't it? So as this one will be rotating about O, so your K2 will be here. It will be only this displacement is a 0.1 power of 2 equal to the K2 prime. You move now K2 prime, isn't it? By the same thing, That's why I keep mentioning just K2, you don't have to do anything. But the same distance, so cancel, you get back the result. So that's why if you found that the the K2 will be no change in distance, so you'll be getting the K2 equal to K2 prime. So you don't have to do the transfer. Just on this one, just to check correct or not. Okay, so you have K2 and K1 correct. Then you have KT here, KT prime is equal to K1 prime is 640 plus K2. They provide you K2 as what do you have for K2? K2 is equal to I don't have a number. K2, what do you have? K2 is 12,000. So you have 12,000. So you have 12,640 Newton per meter. Last but not least, you do all the transfer work, yeah, do one time. This one, the damper. Equation use delta VD initial equal to delta VD equivalent. Then we focus on C1 prime. The C1, the actual C1 multiplied the actual length of 0.2 power of 2 equal to the C1. You move C1 to become C1 prime, you move to 0.5, the new distance here. Because why? Because C1 and K1 is basically rotating about the same fixed point. So you do that, you'll be getting C1 prime here is equal to the C1 is given by 500. This one be 0.2 by 0.5. We're getting the results of 80 Newton second per meter. And you do have another one, C2 is equal to C2 prime is equal to C2, what they provide is C2? C2 is 200, so put it at 200 Newton second per meter. Then you add up together as a normal, additional. We have CT prime is equal to 80 by 200. You'll be getting here 280 Newton second per meter. So as you do this one, the next thing is very easy for you to calculate whatever parameter they ask in the equation. So typically, for example, here they're looking for omega n equal to KT by MT prime. Just pick up the numbers what you have calculated earlier. By KT is equal to 12,640. 12,640 divided by the MT just like 5.133. We get to the result. And you check the result, it is correct as what we did earlier. Okay, I think I'm not going to go further. You can check on your books. So I'm going to skip this one for the calculation. Can I do that? Or you want me to do to continue the calculation, or you can do on your own? Hello? Hello? You want me to continue? Okay. Okay. Yeah. Thank you, Fatin. So the next thing, look at example numbers. I'm intent to expose every single example here, but not in detail as I mentioned earlier, so that you have the idea how to use the solution or perhaps the model of calculation to do the next assignment. Yeah. So if you look at the next one here, next one here, this one. Then we try to, if I have ample of time, we try to solve the exam question. This is coming also exam question couple of years back. So if you look at the equation now, it's also very similar from what we have earlier. So look at the equation. So the system shown here consisting of spring and damper. This one all spring KK and CC, 3K and 3C is displaced and then released, replaced and then released. That one is the normal procedure to get the vibration. So determine the following. One will be TD. What will be the TD? Ratio between the initial displacement and the displacement after one cycle. This one, ratio. So look at here. TD is equal to 2 pi by omega t. So if you expand the equation, it becoming 2 pi. This one be omega n 1 minus zeta square. Correct. So you cannot run away to look at what will be the omega n basically. So to define what be the ratio is basically coming from the equation of ln x1 by xn is equal to 2 pi, n will be 1 zeta 1 minus zeta square. Right? So this is the ratio. Of course, ln here you have to transfer ln to the other side, it become exponential, or exponent. So our aims now is to define omega n again. Omega n is basically k by n. And so you have a choices to solve this one by using analytical or Newton's law, or perhaps by using what? By using what you call it just now is by using Newton's law for equivalent methods. So if you came to solve this one by using Newton's law, let me explain about things here before we move on. Yeah. So look at it. As you displace this one, you displace a bit. Displace. Put it there. Displace. Correct. This one will be theta. Theta. Put it there. You can put this one theta 1. You can put theta 2. Doesn't matter. But if you want to put it theta 1, the other one must be theta 2. One after another. Okay. So if you put this one, for example, for example, theta 1. Or you want to put this one, if you follow better follow the solution, right? Theta 2. Then this one also be displaced, isn't it? This one also be displaced. This one put it there, theta 1. Then you work one after another. You work this one, work out this one, then you go to the next one. So this one is not very difficult. You will have K and C, of course. But if you look at very carefully, you have another K and C, isn't it? Because this K and C will be basically connected to one after another. And this one another K and C. So you will have a 2 parameter which will basically connected from KC, another KNC, and also this one KC. So if you found this one very confusing, you just put it there, K1, K2, K2, and finally K1, K2, K2, it also can do. Or otherwise you keep doing this one as usual parameters. So what you have is summation of moment about O now is equal to I about O theta double dot rotating that way positive. So this one be KC, so K X, isn't it? X will be this part is 0.4. 0.4 means 0.4 theta negative, not to forget, another 0.4. Same thing for C, negative C, 0.4, but not theta, but theta double dot. This one be 0.4. But remember, because we are dealing with this one theta 2, all this one become theta 2, theta 2, theta 2. What else? So equal to IO. IO will be what? Only 2 masses here. Mass of the rod and also mass of this P here. So they provide you the I node here. What this means is they put it at 0.8 plus this one is P will be 4.75. This one is 4.75 multiplied by is 0.4 power of 2. Put in a big bracket, theta double. So that is the only equation involved. Okay, it's not very difficult. If you look at the equation, you will have the equation as such. Can go on this one, do on your own. Inshallah, if you run through step by step, this is the step by step solution to help out student doing this one. And finally, this is the only equation you're going to use to solve every problems. From the 2 equation, one coming from this one coming from this one coming from the rod. Then you merge together, you equate together, you're getting one equation. Okay, I'm not going to do this one detail. You have this one to explain to you how basically we are going to transfer this one from from a complex, perhaps if I may say this one complex system to more reasonable system that easily to be solved. So I'm going to pick up another 7 if I'm not mistaken, sir. It's not this one, this one is later on. 7 6 7 6 7 6. Okay, this one. Use not use Newton's lah. You use equivalent method. Equivalent. Okay, now you have two fixed point. Two fixed point now. Two fixed point, which is O and A. So look for connectivity. So it seems that there is no notation here, isn't it? So just put it A, you got O, you got P, put it M. So look for connectivity. So let M be point of transfer. Then easy to work out, isn't it? Then you know that M will be the point of transfer. So you are going to transfer everything at M now. So then what the next step is, first step is collecting or perhaps selecting what will be the point of transfer. The next thing will be collecting or constructing the complex model to become a simpler model. So the model that we concern here yeah. So you have what? You have M, so put it here, 1, not to scale, yeah. This one is 0.4, put it 0.4. About O. How many mass? 1 mass, 2 mass, 3 masses. So you have 3 blocks. Put it at 3 blocks. 1, 2, 3, and name it M. And I believe MA will not what you think about. M, is it? Doesn't matter. Put it MA, and MA is ME prime, of course. It's not MA. Do another one. MP you have to transfer. Do another one. M what is put it what ROD transfer. This M rod rotating about O, correct. This MP rotating about correct, but not NA. MA is not rotating about O, but yet rotating about A. Put it here. Yeah. Okay. And the distance is 0.1. Do you understand that? Is that clear, class? Hello? Yes, Marcella. Thank you, Marcella Eva. So then what? The system is controlled by, yes, thank you, Cole. The system is controlled by 3K, 1, 2, 3. Put it here. Okay, you have K and C, of course, yeah. Put it here. K is here. C is here. CT prime is equal to, look at CT prime here. This one and this one, you don't have to do anything, isn't it? Because as mentioned by one of your friends just now, this C, these two C's, yeah, is basically located to the connected point or connection point. So you put it just C and C. But this one, you have to work out something, because this one is not at point of connected point. So put it here, put it another point here, and easy for us to, to check, the point is. So you put it there, NCN prime plus, you have C here, you have another C, so you have 2C, put here 2C. Okay, is that clear? Okay, now put it K now. Now K, put it here K now. KT prime, I put it KT prime here, yeah? KT prime is equal to, same thing happened to K. Because why? Yeah? Because you know well that the K and C is always, at one position. Like if you observe this shock absorber, you know what's shock absorber? This is a shock absorber. This one is a plunger. Here you got plunger inside, yeah. Then your spring. Car shock absorber. So it will be what? It will be modeling. It will be model spring and also plunger next to neck, or we call tandemly. So this one, yeah, is a basically absorber. Okay, so KT now, same thing for KT. You have to move KN prime to, you have your 2K here, put 2, you don't have to do anything about it for K. So as this one will be, be one big mass, you have the M total mass. Then you have CT, you have KT. So the question asks us to define what BD. What is just now? Is to define what is the K, if I'm not mistaken, yeah? To define the TD, okay, to define TD. So it's not very difficult then. TD is equal to, TD is equal to omega D. You expand the equation, is basically this one omega N 1 minus zeta square. So you have to look for omega N, you have to look for zeta. How to look for zeta? We have to work out later on, yeah? So now omega N. So before that, you do all the transfer now. So for example, mass equation used is I initial is equal to I equivalent. So I initial, pick up one. Mass is MA, for example, MA prime. So the MA is located here, isn't it? So MA will be MA is, sorry, MA is for this, yeah. So MA is not rotating about O, it's rotating about O. Sorry, rotating about A, rotating about A, rotating about A. So from the this half, the MA, given MA as 8 kg, put it at 8 kg, multiplied by the radius given by 0.1, even though it's not given, put it at R. This one is R square equal to the MA prime multiplied by what? Multiply by the same thing because you maintain the radius, right? So then you have cancelled this one, you cancel this one, you'll be getting the ME prime is equal to 8 kg, 4 kg, sorry, 4 kg. Okay, so now what next is MP prime, MP prime here. MP prime, the MP here, rotating about O is 0.4, so the MP will be 4.75 multiplied by 0.4 power of 2 is equal to the MP prime to the new length of 0.4 is 0.4 pound. So it basically didn't change you anything because you are moving or perhaps transferring the same distance or length. So you'll be getting MP prime equal to 4.75 kg. Then you move on. What else? We have the rod here. So the M rod, put it the M rod prime. So the M rod, if you work out the M rod, yeah, you have 0.4, 0.4 here and also 0.4. So it's basically at the middle, isn't it? It's basically at the middle. Yes or no? Yes or no? And you do know that this one is basically what? Basically what? Is basically uniform. So if at the middle, so how is it if at the middle? How? The rod at the middle. Anyone? Here at the middle, so you have M L squared divided by anyone? Divided by 3 or divided by what? Hello? By 12, correct, by 12. So I can put the numbers here, yeah? I can put the numbers here. Okay, the numbers is M is but very fortunate here, yeah? Very fortunate. So okay. Very fortunate. They do not provide you all the M, but they provide you this one. So just put it as 0.8 is equal to your M rod. Then by K is 0.4 power of. Then you have the M rod is equal to 0.8 divided by 0.4 power of 2. You will get the result of kg. Okay. A bit more, yeah. I want to complete this one before we end our session. M is calculated, everyone. So you have to look for KT now. spring, for example. So what about for the spring? Remember spring delta VE. This one is initial is equal to delta VE is equivalent. So initial one, look at the initial one. So this one we already pointed this one as M. This one pointed this one as N just now, isn't it? So the initial one pick up one. So for example, at N, yeah, Kn prime. This one. So Kn prime is K. K is given by 4,000. 4,000 multiplied by 0.2 power of 2 is equal to, you move this one from N to M. Correct. So you have a Kn power of 2 multiplied by the new length is which is now 0 0.1. The new length 0.4 is correct. 0.4, not to forget power 2. So this one you will have K and you do another one. This one, so your KT now is equal to Kn plus 2K, correct? Isn't it? You have these numbers. Newton per meter. Same thing for damper. Damper and spring, as I mentioned earlier, located at the same place. So you'll be getting the same result here. Sorry, it's not the same result. You'll be getting the same activity here. Damping, this one initial, is equal to damping, this also equivalent. So you work out this one as C here, they provide you C as 100. Put it at 100. This one is Cn prime. 100 multiplied by 0.2 power of 2 is equal to Cn. Now you move Cn to the other side is 0.4 power of 2. You'll be getting Cn prime. Then your Ct prime is basically your Cn plus 2C. Then you have these numbers. Okay, now we are going to look for TD. Shouldn't be any problem. TD is equal to a bit more, yeah. This one is omega n 1 minus zeta squared. Omega n calculated. Zeta is not calculated. So now tell me how I'm going to get zeta. How are we going to get zeta now? Could anyone tell me? How are we going to get zeta now? Because that doesn't mention what. Remember, zeta can always be calculated by two ways. One will be C equal to 2m omega n zeta. The other one is by using the logarithmic decremental, which is xm is equal to 2 pi n zeta 1 minus zeta. This one, they do not provide you. So you cannot use this one. You have to use here. How to use? You have to use equation that Ct is equal to prime, yeah? It's 2mt prime omega n zeta. The Ct here is equal to 2c just now plus Cn prime is equal to 2m. M calculated already. The omega n also calculated already. Then you know what? Zeta. This one calculated, this one calculated. Be ensure that the zeta lies between that one. Okay. Can you proceed with that one, class? There is no way you want to define zeta. It's only to use this one. Remember that zeta can only be calculated by two ways. One is by using the equation C equal to 2m omega zeta. The other one by using the this is the delta, yeah? Delta, remember? Delta is the logarithmic decrementals or the reduction. If you want, it's very difficult for you to remember just one reduction of energy. Sorry, reduction of amplitudes. If the reduction of amplitude based on the logarithm. I think we come to end. I think in the next one, when I meet you again, inshallah, I'm going to solve by another one. This one. This one, yeah. This one is last semester or last 2 semester exam equation. We are going to basically understand this one. Then how is basically the equation in exam comparing to the equation in class. It's not very much different. If you can understand the work here, inshallah, in the exam, you can also do better, because you have to do of course you need to practice. Practicing means what? You have to do all the assignment on your own. Even though your assignment is group assignment, you have so many equations divided by numbers of you, but yet you have to understand, and you have to do on your own the rest when you have the time. So any question before we close this today's session, and we meet again inshallah next week. Next week I'm going to present to you perhaps